Okay, let's move on with the carbonyls. We have in the last class discussed the most simple carbonyls of elements that either have an odd number of electrons or have an even number of electrons. When we have seen that when they have an even number of electrons, we get simple mononuclear carbonyls. When they have, however, an odd number, then we have dimeric carbonyls. So these are, however, the most simple carbonyls only. Carbonyl chemistry is much more complex. There is much more structural possibility. But in order to rationalize these more complex carbonyls, it is useful to know about an important concept in chemistry, which is the concept of isolobality. So this concept was developed by Roald Hoffmann, who won the Nobel Prize in Chemistry in 1981. And he defined isolobality the following way. He said that molecular fragments are isolable if the number, symmetry properties, approximate energy and shape of the frontier orbitals, and the number of electrons in them are similar, not identical, but similar. When you have isolable fragments, then you can likely combine them to form stable molecule. And that now relates to the utility of the concept of isolobality. Isolobality helps us in order to predict stabilities of molecules. It helps us to understand the stability of molecules. And therefore, it is also useful in synthesis because one can identify stable target molecules. Okay, so where does the name actually come from? It comes from the Greek words isos, which means similar, and lobos, which means slope. So when molecular fragments are isolable, then that means that they have similar lobes in the sense that the symmetry properties, approximately energy and shape of these frontier orbitals, these lobes, and the number of electrons in them are similar, not identical, but similar. So at first glance, that sounds very complex, but to apply the concept of isolobality is not so difficult after all. Isolable fragments can easily be derived from the octet rule for main group elements and organic fragments in particular, as well as the 18 electron rule for coordination compounds. So let us first look at main group elements. So for main group elements, as a rule, the number of frontier orbitals is equal to the number of electrons in the frontier orbitals, which is equal to 8 minus the valence electron of the fragment that we are looking at. Okay, so what is an example for that? For instance, when we look at a CH3 fragment, an organic fragment, then this fragment has 7 valence electrons. Why does it have 7 valence electrons? Well, there are 6 electrons in the 3 carbon-hydrogen bond, and there's a 7th electron now in the frontier orbital. Okay, and this valence electron is a radical electron. It's an unpaired electron. Okay, now the number of frontier orbitals is equal to the number of electrons in the frontier orbitals is equal to 8 minus the number of valence in the fragment. So we have here a 7 valence electron fragment. Therefore, we have 8 minus 7 is equal to 1 electron, and that 1 electron is in one frontier orbital, as you can see here. So now this fragment will be isolable to other organic 7 valence electron fragment, because these other organic 7 valence fragment will also have 8 minus 7 is equal to 1 electrons in one frontier orbital. Okay, so what are examples for this? Well, we can, for instance, look at an NH2 group. Okay, so in this case, we also have 7 valence electrons because we have 4 electrons in the nitrogen-carbon bonds. We have an electron pair at the nitrogen, and we have a 7th electron in the one frontier orbital. We can now also substitute nitrogen by oxygen. Then we need 1 hydrogen less, and that gives us an OH fragment. And the OH fragment is also 7 valence electron fragment. Why? Because we have 2 electrons in the OH bond. We have 2 electron pairs at the oxygen, and we have 1 additional electron, which is a radical electron in the frontier orbit. So now, according to the concept of isolobality, we can combine these fragments that are isolable to give stable molecules. So first of all, I would like to say that we can express that 2 valence electron fragments are isolable by a loop, arrow with a loop that symbolizes the isolability. Okay, so it is depicted here. So this looped arrow indicates the isolability between the CH3 fragment and the NH2 fragment. And this arrow here indicates the isolability between the NH2 fragment and the OH fragment. And of course, the OH and the CH3 fragment are also isolable. So now let's combine the fragments and see if the combination leads to stable molecules. So, for instance, we can combine 2 CH3 fragments, and that gives, well, ethane, and we know that ethane is a stable molecule. We can also combine a CH3 group with an NH2 group, and that gives methylamine, which is known to be a stable molecule. And thirdly, we can also combine a CH3 group with an OH group to produce a molecule, which is known to be a methanol molecule, and that, of course, is also a stable molecule. So now we can extend these considerations. Finally, we can also combine, for instance, 2 NH2 groups together, and that gives a molecule known as hydrazine. And we can also combine an NH2 group with an OH group, and that gives a known stable molecule, which is called hydroxylamine. Okay, last but not least, we can even, of course, combine also 2 OH fragments together, and that gives, well, hydrogen peroxide, which is also a known and fairly stable molecule. Okay, so now let's go from 7 valence electron fragments to 6 valence electron fragments. So for instance, a CH2 group is a 6 valence electron fragment. So because this is a 6 valence electron fragment, it has 8 minus 6 frontier orbitals, with 8 minus 6 is equal to 2 valence electrons in it. Okay, now a CH2 group would be isolable with other organic 6 valence electron fragments, not only organic, but also inorganic. So for instance, in H group has also 6 valence electrons. Therefore, it is isolable to CH2. And if you replace nitrogen by oxygen, then an oxygen atom is certainly also a fragment which has 6 valence electrons, because an oxygen atom is just 6 valence electrons. So therefore, we have 2 frontier orbitals with 2 valent electrons in them. So that means they would also be able to combine these fragments to form stable molecules. And let's see if that works. So for instance, we can combine 2 CH2 fragments to give, well, ethene. And we know that ethene is a stable molecule. We can further combine the CH2 group with an NH2 group. So that will give, well, methylamine, which is also known in the gas phase. Okay, even though it's a fairly reactive molecule that has a tendency to polymerize. Okay. Thirdly, we can also combine a CH2 group with an oxygen. And that forms a carbon-oxygen double bond then. And, well, this molecule is known as a formaldehyde molecule. So what other possibilities are there? Well, we can also combine 2 NH2 fragments. So the two NH2 fragments give a molecule which is called diazine. So this is also a known molecule. It's again a relatively reactive molecule, but still a molecule that does exist. And we can also combine an NH fragment with an O fragment, which gives a molecule which is named azanone, which is also stable in the gas phase. Okay, what else is possible? Well, finally, we can also combine 2 oxygen fragments. Well, and then that gives just the dioxygen molecule that we all know. Okay, now let's expand these considerations further from 6 valence electron fragments to 5 valence electron fragments. So 5 valence electron fragment is a CH fragment. So 8 minus 5, well, that gives 3. Therefore, we would expect 3 frontier orbitals with 3 electrons in them. So these CH fragments are isolable to, for instance, a nitrogen fragment, because a nitrogen atom has 5 valence electrons. So therefore, a nitrogen atom and a CH fragment, they are isolable to each other. So for that reason, we can again combine fragments to form stable molecules. So when we combine 2 CH fragments, well, that gives acetylene, which is known as a stable molecule, having a carbon-carbon triple bond. We can combine a CH fragment with a nitrogen fragment. What does that give? That gives actually HCN, which is also a known molecule. And we also can combine 2 nitrogen atoms, and that forms the dinitrogen molecule. So here you see the hydrogen cyanide HCN molecule with a carbon-nitrogen triple bond. Okay, so now we can expand this concept to coordination chemistry also. In this case, however, not the 18 the octet rule holds, but the 18 electron rule. Okay, let's do this. So for instance, the MnCO5 fragment would be a 17 valence electron fragment, and we could determine this by applying our valence electron counting skills. Okay, we can just exercise this again. So for instance, we can use the neutral atom method. So if we do this, then the manganese, which is in group 7, contributes 7 electrons. And then each carbonyl ligand will be treated as a neutral ligand also, contributing 2 electrons each. And well, because we have 5 of these CO ligands, we have 2 times 5 is equal to 10 valence electrons, and 10 plus 10 valence electrons plus 7 valence electrons. That gives 17 valence electrons. Okay, so now we can say that the number of frontier orbitals and the number of valence in that fragment will be 18 minus the number of valence electrons, which is in this case 17. And 18 minus 17 gives 1, so we would expect 1 frontier orbital with 1 electron in it. Okay. Then when we have a 16 valence electron fragment, we would expect that this fragment has 2 frontier orbitals with 2 valence electrons. And we can an example for that is the FeCO4 fragment. And we can again use our electron counting skills in order to verify that this fragment is a 16 valence electron fragment. So the iron is in group 8. Okay. So it contributes 8 electrons. And the 4 carbonyl ligands again contribute 2 electrons each. So 4 times 2, that gives 8, and 8 plus 8, that gives 16. So further, we can consider a 15 valence electron fragment, and a 15 valence electron fragment would then have 18 minus 15 is equal to 3. And because of that, we would expect 3 frontier orbitals with 3 valence electrons in them. All right. So now, with which organic fragments would these organometallic fragments, these carbonyl fragments, be isolable with? So the 17 valence electron fragment would be isolable to a 7 valence electron fragment like the CH3, because both have the same number of frontier orbitals and the same number of electrons in them. Okay, so now a 16 valence electron fragment would be isolable to an organic 6 valence electron fragment like the CH2 fragment, because both of them will have 2 frontier orbitals with 2 electrons in them. And a 15 valence electron fragment would be isolable with a 5 valence electron fragment, where you would have 3 frontier orbitals with 3 valence electrons in them. Okay, now what stable molecules would we expect based on that isolobality? Okay, so we can combine 2 17 valence electron fragments to form a molecule. And in our example of the MnCO5 fragment, we would get, well, Mn2CO5. And we have already encountered that molecule before when we discussed the dinuclear carbonyls. So the concept of isolobality would say that this should give a stable molecule, and indeed, this molecule does exist. However, we can now also combine a 17 with a 7-electron fragment, which would give this molecule MnCO5CH3, and that molecule is also known to exist. And so with this example, we can easily rationalize that this molecule is being stable and that this could be a target molecule in synthesis because of the expected stability. So now what about the 16 valence electron fragment? Okay, so we could combine two FeCO4 units to form this dimeric molecule with an iron-iron double bond. However, nature doesn't realize this because the formation of double bond is not the only way in order to satisfy the concept of the isolobality. In addition, to make metal-metal double bond, we can also make two single bonds within a cluster molecule. And this is what nature prefers. So molecules with carbonyls with metal-metal double bonds are not known because cluster molecules are more stable. Okay, in this cluster molecule is shown here. Each iron makes two single bond to neighbored fragments, thereby satisfying the concept of isolobality as well. So this explains the stability of such a cluster carbonyl. Okay, now what about the combination of a 16 valence electron fragment with a 6 valence electron fragment, which is organic? So in this case, a carbon metal bond is realized. In this case here, in this example here, we have a carbon iron double bond, and molecules with a metal carbon double bond are known as carbene complexes, and these carbene complexes are stable molecules. See again that the concept of isolobality can nicely explain the stability of this molecule. Okay, now what about combining 15 valence electron fragments with each other, such as the cobalt tricarbonyl fragment? So in principle, we could combine two of these fragments to form a dimer with a cobalt triple bond, but again, this is not realized. Nature prefers another solution in which, well, not a triple bond is being realized, but 3 single bonds. Okay? And that gives then a tetrameric cluster. You see that in this tetrameric cobalt tricarbonyl cluster, each cobalt now makes 3 single bonds to neighbored cobalt atoms. So this cobalt, for instance, makes a single bond to this cobalt, a single bond to this cobalt, and a single bond to this cobalt. So this cobalt here can make a single bond to this cobalt here, and this cobalt over there. This cobalt here makes 3 single bonds to this cobalt, and that cobalt, and this cobalt makes 3 single bonds to this one, and that one. Okay, so if we just encountered such a cluster complex, which is relatively It's a relatively complex structure, and I wonder, yeah, why does it form? Why is it stable? You see again that the concept of isolobality nicely explains the stability of the complex and can rationalize why such a structure is stable. So what about the combination of a cobalt tricarbonyl unit with a 5 valence electron unit? In this case, a triple bond is being realized in what is called a carbine complex. Okay, so while cobalt-cobalt triple bonds are not being realized, cobalt-carbon triple bonds can indeed be realized, and we call this the carbine complex. Then, okay, now we can synthesize these tetrameric cluster carbonyls, for instance, through a thermal reaction. So, for instance, we can start out from this dimeric dicobalt octacarbonyl to form our tetrameric cluster in 4 CO molecules. So we basically thermally decompose our dimeric carbonyl, remove CO from the chemical equilibrium, and then we are getting our cluster molecule. So this is a way how you can synthesize such a cluster molecule. So the higher homologues, the rhodium in the iridium clusters, are also known. The RH4CO12 and the IR4CO12. And they can even form spontaneously from the elements rhodium and iridium and carbon monoxide. And that essentially is because the iridium and the iridium directly favor the tetrameric cluster over the dimer here with 8 CO ligands. All right. So there are some structural differences between the rhodium and cobalt compound on the one hand side and the iridium compound on the other hand. So for the cobalt and iridium compounds, we actually have one cobalt which has 3 terminal ligands, and the other 3 cobalts have 2 terminal ligands, and the third ligand is actually bridging, as you can see here. And this is possible because in the cobalt and the rhodium compounds, the metals are relatively close together and have relatively short bond lengths. Whereas for the iridium compound, we have only terminal ligands because the bond distances become too long for the carbonyls to become bridging. So this reflects a general rule that you should know, which is that only 3D and 4D elements can have bridging carbonyls, while 5D elements only show exclusively terminal CO ligands. Okay, then let's continue on that, just on that basis. Need to switch here to the new presentation. Just need to go to the new screen share here. So we can now also understand isoelectronic carbonyl clusters using the concept of isolobality. So in the last class, we discussed charged simple carbonyls. Okay, so we said that, well, when we, for instance, have an octahedral carbonyl, like the chromium hexacarbonyl, then we can make 18 electron analogs by replacing the elements and the respective charges accordingly. So for instance, when we replace chromium by vanadium, then because vanadium has 1 electron less, we need to add a negative charge. And then the isoelectronic carbonyl would be a hexacarbonyl 1 minus anion. So now the same concept we can also apply to the cluster carbonyls. Okay. So we have seen that for the 15 valence electron cobalt tricarbonyl fragment, we can form a tetrahedral tetramer of the composition CO4, CO12. So now what we can do is, well, we can replace the cobalt by a neighbored element, for instance, the iron. So the iron has 1 electron less than the cobalt, and therefore a 15 valence electron element would carry a 1 minus charge. Okay, so now we could combine 4 of these units in order to form a carbonyl cluster. However, this carbonyl cluster is not found in nature, simply because the 4 minus charge would ought be too high of a charge in order to make the cluster stable. So the electrostatic repulsion within the cluster is believed to be too high in order to make this carbonyl stable. So you see here also limitations of the concept of isolobality. While it's useful to predict stable molecule, it also doesn't always work if there's certain circumstances like a too high charge density, like in this case, that prevents the formation of the carbonyl cluster. So now we can also use another method to realize a 15 valence electron compound. We do not change the element, but we actually change the number of carbonyl ligands and just the charge at the metal. So if we actually add to this fragment a carbonyl ligand, then that means that we are adding 2 electrons, 2 valence electrons. Okay. So for that reason, we need to add 1 positive charge, or sorry, we have to subtract 2 charges starting from this here in order to arrive 15 electrons. Okay, so 2 electrons come from the ligand, therefore we have to take away 2 charges from the metal, therefore we go from a 1 minus charge to a 1 plus charge. Okay, now can this dimerize or tetramerize? The answer is no, it also doesn't tetramerize. So first of all, the positive charge actually destabilizes carbonyl in general. But in addition to that, the coordination number also becomes too high. So we have already 4 iron carbon bonds. But when that iron now makes an additional 3 bonds to neighbored irons, we actually get to a coordination of 7. And we've previously seen that a coordination of 7 for carbonyls is not favorable, and it destabilizes carbonyls. So therefore, even though such a tetrameric cluster would be conceivable from the standpoint of isolobality, it is not found in nature. Again, you see here also the limitations of the concept of isolobality. All right. So now the other possibilities. So for instance, we can replace the iron here by manganese. So the manganese has 1 electron less than the iron. Therefore, we have to add 1 electron. And so we go from a +1 charge to a neutral charge. But again, also a tetramer from this fragment is not known because the coordination number will become too high. The coordination number would become 7, and that's very unfavorable for the stability of a carbonyl. So further, we can replace the manganese by the chromium. So the chromium has, again, 1 electron less than the manganese. Therefore, we have to give this fragment here, the tetracarbonyl chromium fragment, a 1- charge. But again, tetramerization would require a coordination number of 7, which is, sorry, not favorable. So what we could also do is we add 1 carbonyl ligand, so that adds 2 electrons. For that reason, we must remove 2 electrons to maintain 5 electrons. So the charge at this pentacarbonyl fragment, which would have 15 electrons, would therefore need to be 1+. So for that reason, we may expect that, according to the concept of isolobality, also a tetrameric cluster may form, but again, it doesn't form because in this case, the coordination number would be even 8, and we have a positive charge in addition, which tends to destabilize the molecules in general. Okay, then what about the 16-valence electron fragments? So we saw that the iron tetracarbonyl fragment is a 16-valence electron fragment, and that is known to trimerize to form a dodecacarbonyl, tri-iron dodecacarbonyl, and this is known to be stable. So again, we can substitute elements, and we can substitute the number of charges. So we can, for example, go from iron to the manganese. Then the manganese has 1 electron less than the iron, because of which we need to add 1 negative charge. Okay, so this is a 16-valence electron fragment, and therefore we could expect that, according to the concept of isolobality, this also forms a trimer. So now will it do this? Well, in this case, indeed, it does it. So the negative charge is actually not too high. It's only 3-, and we have learned that actually weakly negatively charged carbonyls with metal-metal bonds can actually be stable. And again, we see this here, the trimanganese dodecacarbonyl is a stable molecule. Further, we can, well, add a ligand, a carbonyl ligand, to make a pentacarbonyl. But if we do so, then we add 2 electrons. That means that we must go from a 1 negative charge to a 1 positive charge in order to maintain 16 valence electrons. So this fragment, however, is again not forming a stable trimer. That is because now again the coordination number gets too high. We would form 7 bonds. In addition, we have now a positive charge, which is also not favorable for the stability of the molecule. Okay. Now, what we also can do is replacing a manganese by a chromium, and the chromium has now 1 electron less than the manganese, because of which we can remove the positive charge. But again, a trimerization of this compound isn't possible because, again, we would form 7 bonds and a coordination number of 7 would occur, and that leads to the destabilization of the molecule. Okay, we can also go into the other direction, and we can replace iron by cobalt, which is 1 electron more than the iron. That would form a tetracarbonyl, cobalt plus. Does that trimerize? The coordination number would not be too high, but again, the positive charge doesn't lead to sufficient stability of the carbonyl. So there's both destabilization of the cobalt-carbon bond, but also destabilization of the cobalt-cobalt bond with the negative charge. Okay, now we can also remove a ligand and form a tricarbonyl, cobalt minus anion. So if we remove a ligand, well, we remove 2 electrons, therefore we need to add 2 electrons to the cobalt. That changes the charge of the fragment from +1 to -1. So now in this case, that is also not stable. We may argue that in this case, we have a coordination number of 5, which is also not ideal. 6 is always ideal. 5 is possible, but not as good as 6. So for this example here, despite actually we have a modest negative charge, we cannot form a stable compound. All right. So as a rule for carbonyl clusters, we can say that there shouldn't be positive charges and also no high negative charges. There should also not be any high coordination numbers. Okay. Now we can do even more, because we can now substitute carbonyl fragments in the cluster molecules by isolable organic fragments, and that expands the scope of carbonyl chemistry even more. So for instance, we can substitute a tetracarbonyl iron unit within a trimeric cluster, which has 48 cluster valence electrons, by a CH2 group, because a CH2 group, which has 6 valence electrons, is isolable to a tetracarbonyl iron unit, which has 16 valence electrons. Okay, and that actually works. The respective molecule is stable, and again, the concept of isolobality can greatly help us to understand the stability of this molecule. We call this a mu methylene complex because the CH2 group is actually a methylene unit, which is bridging two iron atoms. And we know that bridging ligands always get the prefix mu in the nomenclature for coordination compounds. Okay, now we can even replace two of these fragments by two CH2 groups. And then we have formally an ethene complex that binds side-on to the third carbonyl fragment, whereby the carbon-carbon double bond is reduced to a carbon-carbon single bond, and the respective two electrons in the carbon-carbon double bond are being used to make two carbon-iron single bond. So it's like an ethene molecule binding side-on to this fragment, whereby the bond order of the ethene within the ethene is being reduced from 2 to 1. So last but not least, we could even replace all three 16-valence electron fragments by organic 6-valence electron fragments. And this would then give a completely organic compound, which would be cyclopropane. And this is also a known molecule. It's, of course, a sterically highly strained molecule, but it is possible to make it, and it still has a reasonable stability. Okay, now the same we can also do for 16 in 6-valence electron fragments. So this must be 15 in 5. So this was already 16 in 6. So please correct this. This must be 15 in 5. So if here this tetracobalt dodecacarbonyl, which is made of 15-valence electron fragments of the composition cobalt CO3. So we can replace 15-valence electron fragments by 5-valence electron fragments. And if we do this one time, we get a so-called mu3 methine complex, in which the CH3 group is bridging these three cobalt atoms. Again, we can nicely understand here why this molecule is being stable. We combine 15-valence electron fragments with 5-valence electron fragments. Okay, then we can also do this 2 times. Okay, replace another cobalt CO3 fragment by another CH group. And then we have actually something which we can conceive as a mu2 hepta to ethine complex. So in this case, an ethine molecule with a carbon-carbon triple bond would bind side-on to this dimeric dicobalt carbonyl fragment, whereas the 4 electrons in the carbon-carbon pi bonds would be used in order to make carbon cobalt bonds. So this carbon here would make bonds to this cobalt and that cobalt, and this carbon here would make bonds to this cobalt and that cobalt here. So again, the concept of isolobality nicely explains the stability of this compound. So we can derive this further and replace another 15-valence electron fragment by a 5-valence electron. Then we get to what is called a cyclopropanylium complex, in which basically cyclopropanyl group with 3 pi electrons binds side on to a CO3 fragment. And last but not least, when we substitute all 4 15 valence electron fragments, we get to a completely organic molecule, which is the tetrahedron. So I see we are already a little bit over the time. So let us stop this. Stop the